All right, let's dive right into this high-yield exam review explainer. We're going to completely demystify the absolute hardest concepts in your carbohydrate chemistry chapter. So, whether you're prepping for a massive midterm or you just want to finally understand what on earth is happening inside those test tubes, we're going to break down the chemistry of sugars step by step.
Here's our roadmap for the explainer. We'll hit carbohydrate classification basics, the constitution of glucose, the constitution of fructose, reducing versus non-reducing sugars, the osazon formation mechanism, and we'll wrap it all up with a master's summary cheat sheet. Section 1. Carbohydrate classification basics, the foundation of sugars. We're starting right at the foundational building blocks. So carbohydrates essentially fall into three major groups based on how they break down during hydrolysis. First up, you have monosaccharides. These are your absolute simplest sugars, like glucose and fructose. They literally can't be hydrolyzed into anything smaller. Then, if you move up a level, you hit the oligosaccharides, things like sucrose and lactose. Break those down, and they'll yield a very specific number of monosaccharide units, usually anywhere between 2 and 10. And finally, you've got the heavyweights, the polysaccharides. Think starch, cellulose, glycogen. These guys will yield a massive number, way more than 10 sugar units when they go through hydrolysis. Now, zooming in on those simplest sugars, you absolutely have to know the crucial difference between an aldose and a ketose. It all comes down to the carbonyl group. If the sugar has an aldehydic function, basically a CHO group hanging out right at the end of its carbon chain, it's an aldose. Glucose is the classic example here. But if it contains a keto group tucked somewhere inside the chain itself, then it's a ketose. Fructose is your go-to ketose. It sounds like a tiny detail, right? But this single structural difference is a real game changer. It dictates almost all of their unique chemical behaviors.
Section 2, Constitution of Glucose, Structural Proofs. Let's move on to a total classic exam favorite.
You know, it's actually a fascinating puzzle if you think about it. How do you prove a molecule's structure when you literally can't see it? How did early chemists deduce a complex 6-carbon structure using only test tube reactions, way before we had modern imaging? Well, they used pure chemical logic. The secret to mastering this is treating these reactions as a step-by-step logical sequence. Every single reaction reveals one specific secret about the glucose molecule. Step 1. If you take glucose and reduce it with hot hydroiodic acid and red phosphorus, you get N-hexane. What does that tell us? It undeniably proves that all 6 carbon atoms are linked up in a straight chain. Boom! Step 2. Treating it with acetic anhydride forms the pentaacetate. Penta meaning 5, which proves there are exactly 5 hydroxyl or OH groups present. And finally, step 3. Mild oxidation using brominating water yields gluconic acid. Because gluconic acid is a monocarboxylic acid with the exact same number of carbons, it proves beyond a shadow of a doubt that the carbonyl group has to be an aldehyde, sitting right at the very end of that straight chain.
Section 3. Constitution of fructose, the ketose contrast. Now we're going to contrast glucose with fructose.
So, remember our straight chain test? Just like glucose, treating fructose with red phosphorus and HI yields N-hexane. Straight 6-carbon chain confirmed. But okay, major exam alert right here. Test makers absolutely love asking why bromine water yields 0 reaction with fructose. The answer? It's simply because fructose doesn't have that easily oxidizable aldehyde group. It's a ketose, remember? So, for step 3, if you hit it with a strong oxidation using nitric acid, the fructose molecule actually breaks apart. It forms glycolic and tartaric acids. And because those two acids have fewer carbons than the original fructose molecule, it proves the chain was actually broken at a very specific point. That confirms, for sure, that the ketone group is located exactly at carbon position number 2.
Section 4. Reducing versus non-reducing. Bringing the lab to life. Let's transition out of the textbook theory and get into the actual lab.
This definition is absolutely 100% critical to memorize. What is a reducing sugar? Basically, it's a carbohydrate that can reduce a heavy metal ion in an alkaline or acidic medium, creating a colored precipitate. Structurally, that means it has a free reactive carbonyl group, a free aldehyde or ketone, just waiting to give away its electrons to a reagent. To put that into perspective, let's look at the actual chemistry of Benedict's test. When an aldose sugar is in an alkaline medium, it acts on the blue copper 2+ ion from the Benedict's reagent. The copper actually gets reduced to cuprous oxide, which then crashes out of the solution as a solid brick red precipitate.
And the visual payoff on the lab bench is just so striking. When you see that unmistakable, vivid brick red precipitate,
That's your rock-solid confirmation that reducing sugars are present. Both Benedict's and Failing's tests show this red color. Now you might be wondering, wait, both glucose and fructose give a positive result? Yes, even though fructose is a ketose and doesn't have an aldehyde, the alkaline medium of the test actually causes it to rearrange itself into an oxidizable form, so it still triggers that exact same red flag.
Another absolute classic is a positive Tollens test. When a reducing sugar, let's say glucose, is heated with ammoniacal silver nitrate, something really cool happens. The reduction process deposits actual metallic silver right onto the inner walls of the test tube. It creates a literal silver mirror. Honestly, it's probably one of the most satisfying reactions you'll ever see in a chemistry lab.
But hey, not all sugars are reducing sugars. And this is a massive exam trap, so definitely pay attention here. Disaccharides like maltose and lactose, they're reducing because they still have a free hemiacetal carbon and can undergo mutarotation. But sucrose is the famous non-reducing exception. In sucrose, the glycosidic bond essentially ties up the anomeric carbons of both its glucose and fructose parts. It completely locks up those reactive groups. So because it's missing that free hemiacetal structure, sucrose absolutely cannot undergo mutarotation, and there's no way it's going to reduce your Benedict's or Tollens reagents.
Section 5. Osazon formation mechanism. The boss-level concept. All right, time to tackle the notoriously tricky boss level of carbohydrate chemistry. The osazon formation mechanism is all about tracking equivalents of phenylhydrazine. If we break it down, you can see exactly how a total of 3 equivalents are consumed to create those easily identifiable sugar crystals. Step 1. The sugar reacts with your first equivalent of phenylhydrazine to form a phenylhydrazone. Step 2 is where things get wild, the amidori rearrangement. This creates an alpha-immunoketone. And then Step 3, the grand finale. 2 more equivalents of phenylhydrazine attack the molecule. This forms the final osazone. So that's 1 equivalent in Step 1 and 2 equivalents in Step 3, giving us 3 total.
Section 6, Master Summary Cheat Sheet. Laboratory Results. Let's wrap up this high-yield review with a definitive cheat sheet.
Seriously, you might want to screenshot this right now. This table flawlessly summarizes every single laboratory observation for your monosaccharides, disaccharides, and starch. For example, look at Molish's test at the top. It's yielding a positive result for almost everything because it's a general carbohydrate test. But then look at sucrose right there in the middle. See how it throws a massive negative for Failing's, Benedict's, and Tollens? There is your non-reducing proof staring right back at you. And if you scan all the way over to the iodine test, you'll see only starch gives that distinct color change. It is literally all the data you need right in one place.
So you now have the chemical logic and the lab results to absolutely crush your chemistry exam. But, looking at all these tests, reducing metals to brick red solids, creating actual silver mirrors, forming intricate crystals, it kind of leaves you wondering, how do these tiny, almost invisible molecular differences, like an OH group pointing up instead of down, how do they completely dictate the energy flow of all biological life? From the cellulose holding up towering trees to the glycogen stored in your very own muscles. Keep that expansive thought in mind as you study. Thanks for joining me on this explainer, and we'll catch you next time.